This is the brief on harmonic scalar fields and vector identities. All right, so we're digging into a pretty specific challenge in vector calculus. The question is, what special conditions does a scalar field need to meet to satisfy a really critical vector identity involving a constant vector? First off, the core problem is figuring out when this identity actually holds true. We're essentially asking, when does the curl of a cross product equal the gradient of a dot product? Nailing down that exact relationship is the whole challenge. So what's the secret? Well, the solution really hinges on something called the Laplacian. For the identity to work, the field has to be what we call a harmonic function. And what that means is its Laplacian must equal 0. That 0 value is the key condition, telling you the field is perfectly smooth and stable. Finally, this isn't just abstract math. This 0 Laplacian condition is super important for understanding potential fields. We can even visualize this using the gradient, with arrows showing the direction of steepest ascent. This kind of analysis helps us figure out real-world properties, like the stability of a wave field or how to map the contours of a saddle point. Ultimately, these complex vector identities boil down to one elegant physical requirement. The field must be stable and source-free.